Xinping Hu join us. Xinping is the Associate Professor in the Department of Physical and Environmental Sciences at TAMU at Corpus Christi, and he's also the chair for the Ecosystem Science and Modeling Research Group for the Harte Research Institute for Gulf of Mexico Studies. Xinping also serves as a member of the Gulf of Mexico Coastal Acidification Network, and he is our Science Working Group chair. He's done extensive research in the Gulf of Mexico on acidification, particularly in the west and northwest Gulf of Mexico. And today he's going to be talking to us about carbonate chemistry trends in estuaries along a climate gradient, symptoms, and causes. Thanks so much for being here today with us, Xinping.
Thank you so much, Kim, and thank you for inviting me to give a talk to the college, and it's an honor and a pleasure. My study mostly focused on the carbonate chemistry and in estuaries and also in the coastal ocean. So today I'm only going to talk about things that we found in the shallow water. So hopefully in the future, because we have an ongoing NOAA-funded project looking at acidification in the northwestern Gulf of Mexico. So I hope there will be opportunity to talk about that later in the future. Okay, so first, let me show you the outline of my talk, and want to give you an overview on the characteristics of the estuaries in this region, northwestern Gulf of Mexico, and then followed by acidification in these estuaries. It's kind of a work we have been doing over the past few years. And then also I will talk about the changing role of estuaries in the CO2 exchange between the water and the air. So how that has been changing over the past few decades based on some historical data. Then I'll present the summary. First, let's go to estuaries. For those of you, because I understand the many colleagues, professors, and scientists in USF probably work on the blue water, that is open ocean. So what is estuary? So let me just start with something that two of my former professors wrote in honor of Dr. Tom Church, who was a professor at University of Delaware. And that's what they wrote about the coastal zone. So the coastal zone that they define, or probably in the community, they say, well, coastal zone, as opposed to the blue ocean, is the brown ring around the bathtub. So bathtub being the open ocean. So as you can see, estuaries obviously belong to part of the brown ring. Okay, so that's kind of a little joke. And then indeed, what is estuary? And here you see there's a bunch of different diagrams on estuaries that can be from the top between the sea and the river is kind of open funnel, but then also you have the estuaries that have relatively restricted exchange of water between the coastal ocean and the estuary itself. And then these restrictions can be more or less, and then there's also a lot of variabilities in these type of restrictions. So then the definition of estuaries has gone through many different iterations. Early on, so estuary was defined as a semi-closed coastal bay of water, which has a free connection with open sea. And then the water there is seawater diluted by freshwater. So that's in 1967. And then as time goes on, there's the next definition of estuary is more inclusive or extensive. So that is the partially enclosed coastal body of water, which is either permanently or periodically open to the sea. So you see, there's already more type of estuaries are already included. And then also there is a measurable variation of salinity. It's not only dilution itself. So that definition came from 1981. So the most recent definition, I haven't really kept tracking whether there's another iteration, but then really that's the most recent definition, I think. That's a partially enclosed coastal body of water. It can be either permanently or periodically open to the coastal ocean. And then it receives at least periodic discharge from the river. It's not necessarily has to be continuous. It can be periodic or pulses of fresh water. And also there is a situation where you have this evaporation that is much greater than the fresh water coming in. So in that situation, you actually got hypersaline. So if you compare with definition back in 1967, so it's not really diluted. It's more of very vast range of salinity. So for example, here in South Texas, we can have estuary in, well, there's an example, Laguna Madre and Baffin Bay, salinity can go up to 70 to 80 in some dry years, with very high. So why do we care about estuaries? After all, there's these brown rings around the bathtub. So obviously, well, next week, if some of you go to the SURF meeting, probably you can hear a lot more about estuaries. But then, really, the estuaries are habitats for a lot of organisms and also for humans as well, right? And then they provide the filtering effect and get rid of a lot of pollutants, from the river runoff. They provide a physical buffer, for example, against swamp surges. And obviously, a lot of people, you guys live in estuary region, we live in here, and then the estuaries are providing a lot of recreational and economical benefits to the human society. And then, why do we study the carbonate chemistry in estuary? So obviously, I think, you have a great scientist in USF, Dr. Bob Byrne. I just saw him online, and his lab is specialized in working on the carbonate chemistry and then also ocean acidification. As probably many of you already know, that ocean acidification may interfere with the organismal metabolism, ecology of the ocean, and biogeochemistry. So then, by the same token, ocean acidification has a lot of ramifications. So estuarine acidification may play a similar role. And then that is, probably they can affect the calcifying organisms. And then these organisms may be part of food chain or food web. However, despite of years of study, so there's still relatively little known on the estuarine acidification across the globe, especially, spatial and temporal changes are not very well understood. So that, that's only on the chemistry part. So that the changing water chemistry, carbonate chemistry, the biological impact or ecological impact is even less known. So studies, people recognize the importance of estuaries in terms of a global carbon cycle because it is considered to be a carbon dioxide source from the water to the air. But then there are large uncertainty. And at the same time, people also don't know a whole lot about the temporal changes, given the changing climate, freshwater, hydrological cycle, what these factors play in controlling the estuaries' role in carbon cycle. There's still a lack of knowledge on that. So now let's move into the estuaries in the northwestern Gulf of Mexico or Texas, to be more exact. So Texas estuaries experience increasing evaporation and decreasing precipitation because here we are at roughly 2 to 3 degrees of latitude, but then the freshwater condition change very drastically from, for example, Houston to Corpus Christi. If you ever have driven on the highway from Houston here, you can see the trees are getting shorter and shorter, or less and less at the same time. Okay, so actually the precipitation from the northern part of the coastline to the south decreased by a factor of 2, as you can see here. And then at the same time, there is a greater evaporation. So in the end, if you account for the freshwater balance, you can see, to the northern part of the coastline, it can be a net fresh water coming in. But then if you move to the south, water is getting more and more scarce. So that the availability of fresh water controls the so-called inflow balance. That is basically you subtract the water loss from the water input. So you can see from this contour map from the state agency, Texas Water Development Board, the freshwater balance, even though the precipitation decreases by a factor of 2, but it's famously known, especially from a colleague of mine, Paul Montagna. He has spent his lifetime working on the freshwater inflow issues. And his word is that, well, precipitation decreased by a factor of 2, but then freshwater balance actually decreased by a 2 orders magnitude. And because of the changing freshwater conditions, the water residence time actually can vary significantly. As you can see from this figure, it's kind of a grainy. I copied from an old book. You can see these are different estuaries around the Gulf and different, let's see, let me move this, okay. the residence time of these different estuaries. And now we look from the northern part of the coastline, Spin Lake, that's in between Texas and Louisiana. So a few days of residence time, and then move to Galveston Bay, increased to about a month or two. Then Matagorda Bay, that is over here, along, well, that's Spin Lake, I forgot about the pointer, Galveston Bay, Matagorda Bay, and San Antonio Bay to the south, and further closer to our region. So this is Mission Aransas estuary, so Aransas Bay over here. Then Corpus Christi Bay, that's the one, this red dot, that's where I am right now. You can see that the residence time of the water in these estuaries got extremely long as you move along the coastline to the south. And here you can see this is Tampa Bay. Just as comparison, also Tampa Bay at the same time is fairly large compared to what we have here. So let me talk about acidification in these estuaries. And every time when before that, let me give you a brief overview on what I'm going to talk about on the alkalinity. So alkalinity, for those of you that are chemists, you probably already know this, but then for those of you that are not, don't sweat. And just alkalinity is by definition, is a pretty daunting, long equation. But at the same time, in most of natural waters, what you see in alkalinity really that's mostly bicarbonate, which is if you dissolve the baking soda into the water, that's the alkalinity, and a little bit of carbonate. So they are called the natural antacid. So the alkalinity in the rivers and in the ocean, a lot of it comes from the continental weathering. So if you weather the rock and then dissolve and then wash down through the river streams to the ocean, so that's where the alkalinity comes from. So these are the dominant alkalinity species in the natural waters. And the other thing is for alkalinity, if you mix the river and the ocean, and if there's no reaction going on, you would typically get a straight line between alkalinity and salinity. So that's what we call the semi-conservative. But then this relationship can be indeed altered by reactions like photosynthesis, respiration, and carbonate precipitation or dissolution. Or you may have other acid-base reactions. For example, acid deposition from the air will alter alkalinity in the coastal region as well. So this acid can be from shapes that consume the sulfur-containing oil or fuels. All right. So now let me show you one of the very first figures I plotted when I learned, I got here in 2012 to join the university, and then I was looking around just to see, what I can work on. So I talked to a colleague, Paul Montani, asked, do we have any historical data? Then he said, well, yes, we do. And then so he handed me this bunch of data. So that is actually alkalinity data in the entire Texas coast in all these estuaries. This is a very rough plot. That's first plot I generated. And then, statistically, there is a significant decrease trend across the entire coastline of Texas. You can see the data started from about 1970s, and it stopped there. That's as when they had the data set. But then this data actually is continuing because the agency, the Texas Commission on Environmental Quality, they are collecting the data still in the broad coastline here. So on the y-axis, you can see the number is, doesn't mean anything unless you give it a unit. So the number is actually alkalinity in the unit of the milligram of calcium carbonate per liter. So that's basically ppm. And then you can convert that to alkalinity value by multiplying 20. So that'll give you 20, certain micromole per liter in this case. So then because of this long-term decrease, I define this as not necessarily acidification, but then de-alkalization of the estuary waters. So let's move forward. So this is the paper we published back in 2015. And on the left, this is basically an overlay between 1970s and the first 10 years of the 21st century. We just simply subtracted the 1970 value from the 2000 value, and you can see all this green color shows a net decrease of alkalinity in these estuaries. Just a few spots you may have this slight increase. And also we plotted the alkalinity reduction rate and then correlate that with pH, well, there's a significant correlation. You can see, when you have the greater decrease in alkalinity, there is greater pH decrease as well. So, and again, here, just the arrow shows when you move from northeast to the southwest, and the climate is getting drier and drier. And if we look at the pH change across these estuaries, then compare with what people have seen, well, including one of the Dr. Burns studies in the open ocean, the observation was over the past a few decades, the pH decrease has been hovering around 0.02 pH units per year. So you can see the majority of the Texas estuaries, they have a greater pH decrease. And also at the same time, if you look at the Tampa Bay, so this is actually from a study published by Lisa Robbins several years ago. So they looked at the pH trend across the Florida estuaries, and you can see the pH decrease is a lot smaller. So I'm going to talk about that a little bit later today. So what happened to alkalinity? So if you look at the estuary as a box, and there is input, which is coming from the land mostly, and then there is also exchange between the coastal ocean and estuary. And also there may be benthic processes that can alter alkalinity in the estuary. And after all, estuaries here in Texas are mostly a few meters deep. They're not really deep. Okay, so if we look at the, very simple conceptually, the mass balance, we have the supply and we have demand. And we have to assume that the exchange between the estuary and coastal ocean has remained constant, more or less. So then what happened to supply could alter alkalinity. So let me show you what I got. But then before we go into the detail, and I just want to show you the city water quality report that I got from the two different places. So here, this is the latest water quality from Corpus Christi, the utilities department. And if you look at the alkalinity of our city water, you can see the average concentration of alkalinity is 180 ppm. So again, here, to convert the ppm alkalinity, ppm of calcium carbonate to micromole, you just multiply this by 20. You get a micromole per liter of alkalinity, so that you can see if it's 150 multiplied by 20, they could give us 3,000. So this 3,000 micromole per liter of alkalinity is greater than what we see just offshore from Texas, 2420 micromole per kilogram at a salinity 36.4. So, when I first saw the report, I was pretty amazed because I never imagined the city water could be so much alkaline than more alkaline than the ocean water. So anyway, and then I was curious to see, what you guys have there in Florida, and then, but then it's also a little surprising because I was expecting a little lower alkalinity. So you can see here, your alkalinity from last year was 120 milligram per liter, and then convert that to micromole, multiplied by 20, that's 2,400. So you have a little less acid buffering capacity in your city water, but then still that's fairly high compared to a lot northern states, Georgia, Virginia, those places. But then also, if you're interested, compare the mineral content, we do have higher mineral content than you as well. So I would joke with people, if you have heartburn, you can drink the high alkaline water or soda water. This is basically soda water, can quench the excess acid, hydrochloric acid in the stomach. So let's move forward. And then, what may have caused alkalinity if you look at the supply side. And here, this is the summary we did back in University of Georgia when I was doing postdoc. And we basically summarized the ocean margin alkalinity distribution across these different rivers, all the way from Mississippi, Amazon, and then we went actually up to the Arctic. So you can see there is a fairly large range of river alkalinity values. All right, so that was back, more than 10 years ago. Then this was a few years later when I looked at the river alkalinity values. And so TCEQ, the Texas EPA, not only measure alkalinity in the estuary and coastal water, they also measure across the entire river network. So you can see that river alkalinity has fairly large distribution or range in terms of the values. You can see the entire western North Atlantic ocean margin come to Texas is only a small fraction of the axis we're looking at. And this corresponds to, again, the climate conditions. So as you move from the north to the south, the river alkalinity is getting higher and higher. So that's fairly fascinating thing that I saw when I first looked at the data. Okay, so let's look at the rivers. And on the bottom panel, you can see here, so this is the history of the Texas population up until the recent decade, and the last two columns are just projection. So this is based on census data. And because of the increase in population, there's increase in industry and a lot of other things, agriculture demands, there is really a need for keeping the water on land, building a reservoir and keep them there. And if you haven't heard, Tesla is just decided to move their headquarters or plant, I don't remember, to Texas not long ago. So because of this requirement of fresh water, so dams have been built just to keep water on land. But then at the same time, if you have the river water preserved in reservoirs, and then they will produce calcium carbonate because the chemistry determined that calcium carbonate will be precipitated out of water column. And then if you have been to any of the western states, look at the reservoir, if the water level is low and the wall of the reservoir is coated by this white minerals, that's mostly calcium carbonate. So by forming calcium carbonate, actually consume alkalinity. Okay, so that is why if you keep the water in the reservoir for long enough time, then it'll reduce the level of alkalinity in that river, in that water. So once that river, the water flows down to the river channel, you're going to get less alkalinity compared to what it got in the beginning. And USGS scientists, TEPSTATS, they studied the water alkalinity, river alkalinity, and then this is actually one of the result they got for Brazos River. That's the largest river in Texas. You can see over time there's a gradual decrease in the alkalinity level in Brazos River. Right? And also at the same time, we also measured, I asked my student, why don't we just use a similar technique and see, Ted stats, he mostly did the nationwide large rivers, and we want to look at all these smaller rivers in the state, how these rivers have been changing over the years. And then one of my students, she did this data pairing. She used the flow data from USGS and used water quality data, which is alkalinity from TCEQ. And then she did extensive work on analyzing data and then apply the USGS flow model, the load estimator model, and then use the non-parametric candle correlation just to find out whether there has been any changes in the water chemistry and the discharge. And the three parameters were looked at. So she looked at the flow weighted concentration. So that is basically adjust the concentration with flow. And then this is actually, if you get flow weighted concentration, that is irrespective of the amount of water flowing down, because of the flow adjustment. So the second parameter she looked at was the area weighted yield. So that's basically total load of alkalinity divided by the area of the watershed. So that indicates the extent of alkalinity production on the basin scale. And of course, the discharge is pretty straightforward, just the water flow trend over time. And I'm just going to show very simple a few figures that she made. You can see that the first plot is the flow weighted alkalinity concentration. Other than Spin River, a lot of other rivers, they don't show temporally significant trend, but then Trinity River, that's one of the largest rivers in Texas, there is a gradual decrease in the flow weighted alkalinity concentration. So the second plot shows area weighted alkalinity yield. You can see these rivers in the north, they don't have a trend, but then for Colorado River, that's another large river in the state, and Aransas River, they have seen area weighted alkalinity yield going down over the past few decades. And then at last, this figure shows the net discharge. So all these rivers up north, they don't show much, but then Aransas River is kind of smaller river. the major tributary to Aransas Bay. So there is a long-term decrease in the freshwater discharge. So putting this together, we basically can conclude that in the northern part of the state, northern estuaries, this reduced river alkalinity export both reflected through the flow-weighted alkalinity concentration and area-weighted alkalinity yield, and they show a long-term decrease. So that is the reason for alkalinity decrease in the northern part of the coastline. And then at the same time, if you go to the south, the reduced flow of the water, and remember that the further south you go to, the higher the river alkalinity. So if you reduce the amount of river alkalinity input into estuaries, naturally you would see lower alkalinity in the estuary, right? Because the ocean water has lower alkalinity. So that's on the supply side. And then also we need to look at the demand side. So the reason of doing so is because of what we saw. Let me show you here. So this, the conjecture was, well, not only you may have the decrease in the supply, but then because water is so shallow, and then there's water residence time can be pretty long, up to a year. And given the shallow water, and there may be plenty of opportunity for things to react. So, and just to show you the theoretical part of the reasoning, and here you can see, this is the river and this is the ocean. As I said, alkalinity is semi-conservative. If you have no reaction going on, you would expect to see alkalinity distribution follow this pretty straight line between the river and the ocean. Okay, so these two dashed line or dotted lines represent evaporation or precipitation. So that is because it goes through zero. Okay, so if you evaporate the ocean water and go hypersaline, assume there's no reaction occurring, you would follow this straight line so that alkalinity to salinity ratio would be the constant, right? But then if any data point, for example, estuarine water parcel stays here, if you evaporate, it would follow the same line that goes through the origin, right? So that would be evaporation line. But for any estuary, when you have a river end member, you have an ocean end member, if no reaction happens, the lowest slope or the lowest alkalinity to salinity ratio would be the ocean, right? So let's see. Yeah, so that's when you have the estuarine water evaporate, and this slope or the ratio of alkalinity to salinity would be greater than the ocean. And we call this slope as the specific alkalinity. Actually, it's the term that was used ever since 1960s. So without the reaction, the slope of the seawater evaporation and precipitation line would be the lowest, or the ratio is lowest. And then if you are in the estuary, so wherever you are, as long as the salinity is not up to the ocean level, the ratio of alkalinity to salinity would be greater. Okay. So anything, if you have a mixing line or the evaporation line ready there, so any data point, for example, data point falling behind or below this line, that would indicate, well, there may be a process that consumes alkalinity. So, and actually, this is what we saw using the TCEQ data. You can see the y-axis actually shows the log value of the specific alkalinity, and the horizontal line represents Western Gulf of Mexico surface water. You can see in a lot of cases, when salinity is high, there is a significant decrease of the specific alkalinity or alkalinity to salinity ratios that indicate consumption. Right. So if you look well, this is again Texas coastline, and then here are a few stations in the Mason Aransas estuary. So this actually is part of the National Estuarine Research Reserve Network, and we sampled for quite a few years already. But then there was a dry year when we took the alkalinity samples and salinity in these 5 stations, and this is a very dry period, and you can see alkalinity as time goes on. There is a decrease in alkalinity, and at the same time, increase in salinity. So if you remember the theoretical reasoning, if there is no reaction, if you evaporate the seawater, you would see the increase in alkalinity. Here we see the opposite trend. And then if you divide alkalinity by salinity. So actually, this also decreased to the point of below the seawater level. So that indicates, well, something must have happened to draw down the alkalinity. So in this period, and then we took this data and then did a simple mass balance calculation. So that's what we did. From this May till early September, excuse me. So there is very little river coming out, and then we kind of took each station, considered water stagnant. From time 0, time 1, time 2, time 3, all the way to time n. We also account for salinity change because this increase of salinity shows the evaporation effect. Then we also, because we measure calcium all the time, and then we also have the alkalinity. So basically what we did was to correct for the salinity change and calculate how much of calcium change correspond to how much of alkalinity change. Then construct the two parameters together and see whether we can see any kind of a stoichiometry. And this is what we saw here. So the equations, is basically we consider a concentrating effect, then compare that with observed data. So the difference would be because of reaction. So then if we plot them together, you can see the alkalinity change on the y-axis, and then calcium concentration change on the x-axis. Right, so that's what we saw for the innermost station, moving out all the way to the ship channel. So you can see all these slopes are fairly large compared to what you would expect for calcium carbonate formation. So if you have calcium carbonate formation, the reduction of calcium and alkalinity would follow a 1:2 ratio. Or if it's alkalinity to calcium ratio, it would be 2:1. But instead, we saw much higher alkalinity drawdown per unit of calcium drawdown, which means not only calcium carbonate formation may be responsible for the alkalinity reduction, but then there may be something else that we didn't know. So then we collected sediment samples, you can see here, from the same estuary, and then kind of the cap of the core was closed for just a couple of days, and look at the top part of the sediments. So to me, that indicates there is plenty of iron, because iron sulfide is black, as I don't know, probably in Florida is less so because there's not so much of iron. It's a carbonate platform. Here we have heterogeneous sediments, and there's a lot of iron sulfide in the sediments. So then we did a very simple sediment incubation experiment. Basically, we have this core there, and then we fill up to the top with water. Then we stick in a stirrer, and then just stir that for a few weeks, and just to see what is altering the water chemistry. And we measure magnesium, calcium, sulfate, and alkalinity over time. And this is some preliminary data. There's still some data coming in. And you can see over time, adjust for salinity change, because obviously if you evaporate the seawater and sulfate and the salinity would go together. But then here we correct for salinity change. There's a still significant increase in the sulfate concentration, which means probably those sulfide may have been oxidized and then contribute to the sulfate in the water column. And then this is also very simple mass balance calculation. So from these few different parameters and change in magnesium and calcium, we can safely say, well, that's probably because of dissolution of carbonate, and that would contribute to alkalinity. But then at the same time, if there is a sulfate production, which means sulfide oxidation, that produce acid. So actually that gives us a negative alkalinity. And overall, this core, with the salinity increase evaporation, the benthic production of sulfate, that's more than enough to compensate the dissolution, and then we have a negative alkalinity in this core top in the water. So mechanism we are trying to propose is that, well, here this is for an estuary with a lot of fresh water. Okay, so there is a fresh water coming in, you have a production. So production of organic matter, the organic matter gets preserved in the sediments, and then these sediments may go through both aerobic respiration with oxygen, or when oxygen ran out, a little bit underneath the surface sediments, you have the anaerobic reaction. You have nitrate, and there's iron oxide, and then there's sulfate. So then this reaction will lead to anaerobic respiration lead to a production of nitrogen through denatrification, and then sulfate iron reduction give us the iron sulfide. Okay, so that's what we see in this kind of a situation. You have the iron sulfide accumulation in the wet conditions. And at the same time, if there is a freshwater, you turn off the freshwater faucet, then you don't give it fresh water, then production may decrease, and then you don't have so much of the production anymore. And so this create a situation where you could stir up the benthic sediments and then let the reduced sulfur to oxidize and release acid. So for here, you can see the top part is iron sulfide in the reduced form, but then in the nature, so that's actually top part of the sediments shows this rusty color. That's to me that's oxidized iron. Okay, so that's the contrast between wet and dry conditions, right? So this oxidation of sulfide give us the proton or acid to titrate alkalinity down. So the reason we think this is happening is because this is national wind field data. You can see the purple color represent the highest wind speed. Entire central part of the US and including parts of the Texas coast, we have fairly high wind speed. And believe it or not, in Corpus Christi, we have annual wind speed 50 miles per hour. That's annual. So we have calmer days, but then not so many compared to where you guys are in the eastern part of the Gulf. So all this wind and combined with shallow estuaries could stir up the sediments, and then this can expose the reduced minerals. If there's not so much organic production, reduced minerals could be oxidized and release sulfate. And especially if water stay in the estuary for over a year, you can imagine, if you shut off the fresh water, and this could create a situation where you just created a lot of acid production in the sediment water interface or even in the water column. So that's why we observe the decrease in alkalinity in these semi-arid estuaries, especially to the south. So the situation with this is that, well, here, this is the river-ocean mixing again. And here is the evaporation of ocean water. And in the dry conditions, all right, it goes to hypercilium, and then alkalinity can be consumed. You have this new alkalinity in this hypercilium environment, but then what if you have a sudden release of fresh water? This will create another mixing line. You can see the alkalinity across this entire salinity gradient is lower than what you would expect for a normal condition where you have not so much of hypersalinity and not so much of alkalinity consumption. So this will create a less buffered estuarine water. So when this type of condition happens, it could create much less buffered estuarine water. And then because salinity is considered as a stressor, especially if the salinity is low, so these two factors could work together to decimate calcifiers living in this estuarine environment. And just to show you how dramatic the freshwater can be, either we're dry or we have the heavy rain and very fast heavy rain. So that's pretty extreme. And then in the future, also, we need to look at the future climate projections. All right. So the projection says, well, in the southwestern US, we're going to see a drier and drier environment. But then it doesn't mean that it's dry all the way. We may still have these pulses of fresh water. So this situation, if it persists, it would give us, swings in carbonate chemistry in the estuaries. We may see even more extreme conditions. And also the other thing is with the dry and dry environment, then what if the hydrology changes on the coastline and the chronic shortage of fresh water becomes the issue for those areas that may not see that in the past few decades? This could have some implications towards the buried organic, buried reduced sulfur in the sediments. All right, so I'll spend a few minutes talking about another part of the research, looking at the CO2 partial pressure evolution along estuaries. So first, let me just show you here. This is actually a synthesis that my former postdoc mentor wrote 10 years ago. And this is basically a CO2 exchange across the entire ocean. You can see a surface ocean that's 2 orders of magnitude greater, well, 1 order magnitude greater than the shelf, and then the shelf is 1 order magnitude greater than the estuary surface area. So that surface ocean and estuary, they're 2 orders magnitude different. In terms of air-sea CO2 exchange, we know for the fact that open oceans is a net sink of CO2, and the continental shelf is also a net sink combined globally. But then also we are confident to say that estuaries are a source of CO2 to the atmosphere. But then there's, of course, there's large uncertainty. But that's kind of a static view. So how these estuaries evolve along with time, is really not well known across the globe. Here's where our work comes in. Let's look at all these estuaries again. So this is Lavaca, Colorado estuary, Guadalupe estuary to the left, and then Mission Aransas, Ulysses estuary, Corpus Christi Bay, all together. And we have done a few years of sampling in these different estuaries, and I want you to look at the bottom panel. That's my student published last year. So you can see, that's the PCO2 of these estuaries, and there's of course seasonal variations, but overall you can see for the most part these estuaries have higher, PCO2 than the atmosphere. And then at the same time, if you look at the fluxes that we calculated, here this is 0, you can see over time, these estuaries have greater or positive flux from the water to the air. And we know for the fact that these estuaries, overall, they are a CO2 source to the atmosphere. Now to look at the long-term changes in the PCO2, we have to work with the historical data. So the thing with the historical data collected by agencies, is that really the precision may not be that great. And for example, alkalinity is plus or minus 5%, pH plus or minus 0.1. And compared to what we are usually accustomed to in the modern days, for example, Dr. Burns' lab and also in our lab, we would typically look at the precision of 0.2% or 0.1 to be better. Especially in Dr. Burns' lab, and then pH within plus or minus 0.001. So this data, the agent's data has cruder precisions, but then we could work with it. But first of all, we need to be rigorous in terms of selecting the data. Here what we use, we choose the more than 20 plus years record. Then they all have to have seasonal data at 54 stations. Then we went through this very rigorous outlier removal procedure to get rid of the outliers or potential outliers. Then we consider propagated error based on the input of the alkalinity range and pH imprecision, so to speak. We come up with this error for PCO2. All right. So then what we did was, you could use this robust regression called thiosin regression. That's pretty robust against the outlier. And then we also did another set of resampling. You have this range plus or minus of the propagated error. And in this range, we use the computer program to select randomly 1,000 times. So for each station or each data point, we select 1 time. Okay, and then for the entire time series, there's 1,000 iterations of this calculation, and all these values were averaged together and then obtain the 95% confidence interval. So then we compare the 2 sets of the regressed slopes against each other just to see how well the regression works. So these are the stations that we picked from across the entire coastline. And this is kind of a very busy figure, but then I want to show you that. So the orange data points are basically the simple, this is a simulation, the resampling of the data points, and then the blue data points are just from simple regression. You can see that by and large, most of the stations don't show much of difference for these 2 methods. So which means the thiosin regression is pretty robust, except in just a couple cases. Okay, so, but overall, you can see out of all these stations, 54 stations, almost one half of the stations, so pretty significant PCO2 increase over the years. As a handful of stations shows the negative slope. And then 23, just the data don't give us enough statistical power to get a meaningful trend. But overall, for this positive trend, you can see the rate is between 2 to 26 microatmosphere per year. And then for the next trend, just a little bit slightly negative, actually. And then also, if you look at the coastline, and remember the northern part of the coastline has more fresh water, and the southern part has less fresh water. So if you have more fresh water, it appears like, well, for Galveston Bay, there's greater slope increase, I mean CO2, PCO2 increase, up to 26. Now let's look at the comparison. So several years ago, one of my students published a paper, looking at the global ocean margin CO2 level, and then she concluded that, well, over the entire globe, all these coastal margins have the PCO2 increase roughly around 2 microatmosphere per year. And then recently, a colleague at College Station, Katie Schemberger, her group published a paper. You can see in the coast of Texas, there is an increase of 3.2 microatmosphere per year. So that's based on 1996 to 2017 data. And then here, this is the PCO2 trend we observed in Texas coast. This line represents the coastal Texas. You can see the vast majority of the stations in Texas estuaries have greater PCO2 increase over the years. So we just submitted this paper not long ago. All right, so based on the fact that we know these estuaries are a CO2 source to the atmosphere, and then also we see the greater PCO2 increase over the years, then we can confidently say that, well, these estuaries probably over the past few decades have become a stronger CO2 source to the atmosphere. All right, so just a little bit on this mechanism. This is not definitive, but then I was interested in what may be controlling the CO2 trends. And if you look at the temperature trend data, so that's actually from the Texas Parks and Wildlife Department. So all these agencies, they collect, good quality data. And you can see that the cross coastline, actually here, the bluest is still zero. You can see more or less all these coastal estuaries demonstrate some kind of a warming, in greater values or smaller values. And if you look at these two, that is Matagorda Bay and the Corpus Christi Bay, so they have very high increase rate in terms of temperature. So there is the majority of stations, the pink color represent a positive PCO2 trend. And in comparison, if you look at Galveston Bay, the temperature increase actually wasn't so severe, relatively speaking. But the PCO2 there appears to be increasing much faster than the other part of the coastline. And then I went to the, Galveston Bay Estuarine Program, and then they publish, every so often they publish these state of day reports. And the most recent I found was in 2011. And you can see that in Galveston Bay, there's from 1980s to the 2000, late 2000, and you can see there is a decrease in the salinity. And also at the same time, there's a decrease in the chlorophyll concentration. So to me, considering there is an increase in the PCO2, it seems like there is a net decrease in the net ecosystem metabolism. So that actually contributed to this increase in the PCO2. And by the same token, in Tampa Bay, if you remember, the pH decrease is a lot less than estuaries here, and also than the open ocean. Actually, this morning, Dr. Yates talked about the seagrass restoration. So this seagrass restoration may have buffered this acidification trend quite significantly. Okay, and again, so here, let's come back to this usage data. This really the data, I was expecting to see something that is interesting, and then it's indeed is as interesting as I first imagined. And we use this relatively not so precise data from the state agency, and we examined the PCO2 trend based on alkalinity and pH. So this is really promising because I believe across the country, there are still a lot of data that is probably hidden that needs to be dug out. And then also, because of all this effort, really the society as a whole really need continued sponsorship of these kind of programs. And even probably citizen science, combine all the resources together so we can have a better understanding of the changes in the coastal carbonate chemistry and also on the ecosystem. All right. So at last, let me summarize. I'm kind of running slightly behind. And just the summary, so we have this long-term estuarine alkalinity decrease. So it can be caused by a decrease in river alkalinity input up north in the northern part of the coastline. So that's a decrease in the river alkalinity level. And also to the south, there is a declining river discharge, especially from the high alkalinity rivers. And also in these hypersaline conditions, alkalinity consumption can be significant. Because of the decrease in river discharge, you increase the the estuarine residence time so that there's plenty of time for reactions to take place. And then also there's benthic pelagic coupling because of oxidation of sulfur and produce acid. So the sedimentary processes, including calcification, may both contribute to the alkalinity decline in these estuaries. And also we have to consider in the future if the climate change, the reduction of the freshwater, in that sense, and also with the pulse of this flooding water coming down, whenever we see the storms, and then it could cause pretty drastic swing in carbonate chemistry in these shallow estuaries. And also at last, based on this government data, agency data, we concluded that northwestern Gulf of Mexico estuaries have become a stronger CO2 source to the atmosphere. And we attribute this to probably warming contribute to somewhat to this CO2 increase. And also the estuarine metabolism definitely may have changed as well. And also we would really like to see, other colleagues working on probably dig out the agency data and just to see what we might have missed or what we might be able to discover from all these great data repositories. And in the end, I would like to acknowledge students and technicians and postdoc and former students used to work in the lab and colleagues. They have provided a lot of help to our past years of work. And also we have relied heavily on the UTMSI just to cross water from my office. Mission Ranches National Estuarine Research Reserve, colleagues there and students, and especially Dr. Byrne, he was a collaborator on our NOAA-funded project several years ago, and Alan Shearer helped us to run some elemental analyses. But ultimately, a lot of this work cannot be done without the data from the Texas Commission on Environmental Quality. And with that, I would like to end my talk, use the aerial photo of our university. If you have never visited, I would encourage you to come. And if the students, you're bored of Florida, which I doubt, you can come here to study. Thank you.
Thank you, Dr. Hu. So we have some time for questions, and we'll start with any student questions. Feel free to either type it in the chat, or if you're able to unmute and ask a question directly, that's fine too.
Howdy, Dr. Hu. My name is Dylan. I actually just finished my undergrad studying oceanography at Texas A&M College Station. So to hear you bring up Dr. Schamberger was a taste of home. Great talk, very linear. I appreciate it. What anthropogenic considerations did y'all make when doing this carbonate chemistry? The influence of the Houston ship channel kept coming to my mind in Galveston Bay. Did y'all spend any time in that headspace?
Well, that was actually after after Harvey, we went up there for almost a year, looking at the carbonate chemistry there. So my student, Larissa Diaz, she's actually working on manuscript using that data. So I haven't seen the outcome yet, hopefully soon. I hope I can update you probably in half a year.
Totally understandable. Thank you again.
Thank you.
Any other student questions? And if you have your hand up, go ahead and unmute because I'm monitoring the chat at the same time and I can't see both.
Yeah, Brianna has a question. Go for it.
Hi. My question is actually kind of related to Dylan's question in a way. I was wondering when it comes to the decrease in alkalinity and this and it being possibly related to, if I understood correctly, the kind of drought and then flood and resuspending of sediments and things like that. Have you considered or have you gotten a chance to look at all at especially when it comes to when you showed that figure at the beginning of certain estuaries, we're seeing that decrease in alkalinity and certain ones weren't. Have you looked at all at kind of land use and especially like substrate hardening, possibly increasing the flood intensity in terms of you were mentioning population increase and things like that, and so I'm wondering if there's been this increase in substrate hardening in certain areas, maybe not others as much.
Right. So that's actually a great question. We haven't thought about the substrate hardening, but then if you recall the southern part of the coastline, we do see the decrease in the area weighted alkalinity, which means there may be less weathering product coming off from this watershed. So hardening can certainly be one of the causes, so that you don't have so much of the rocks or soil exposed, and then there is a potential reduction in this weathering process. So yeah, you're right, but then yeah, we haven't looked at that. Thank you though.
Thank you.
Any other student questions? And also faculty questions and other participants. I see one hand up. Go ahead and unmute and ask your question.
Hello, my name is Boris Galbrin and I'm a faculty here, a physical oceanographer. I have a question to you about the factors which affect the distribution of alkalinity in this case. You mentioned the decrease in the freshwater runoff, but you have also equivalent effect from dredging of the rivers to deepen the, say, navigational channels. Because when you do this, you increase the salinity intrusion on the bottom. And it will be equivalent to reducing fresh water because salinity goes farther away than the fresh water can go. So it didn't mention anything of this, but I think it will also have a significant effect, and you needed to include this factor among other factors which you considered.
Yes, I agree with you. So dredging, here, for those of you that are not familiar with this area, that's because here that's the bottom is muddy and soft, and then we do have the ship channels at various places. So dredging has to happen every so often to keep the channel clear. So yeah, dredging could have impact on the total salt content in estuary, but then on the other hand, I would say that ship channels, while they do affect the circulation in estuary, but at the same time, total volume-wise, I'm not sure how significant that would be compared to the entire estuaries in different regions, but certainly it's possible. But the other thing I thought about was, dredging definitely brings up the mud. That's something I was thinking about doing. The mud may have this reduced sulfur. If you bring up this mud, and then this could create the condition you expose the reduced compound to the air. So that's another opportunity for creating this acid. So that's great point of the dredging. Yep, it's something I was planning to look at.
All right.
Thank you.
Thank you.
Yep. I see Frank.
Go ahead, Frank.
Hi, Xinping. Great, thank you.
Frank.
Great talk. I'm glad that you're doing this. And there's so many misconceptions and questions about how these estuaries are changing, and then they're changing because there's a lot of people and sea level rise and also. So I was wondering, I think that you mentioned the word metabolism, but you didn't mention biology or life growing in the estuaries.
Right.
So,
well, I potentially in the audience there's a lot of biologists. I just couldn't, I dare not to brag too much. But,
I mean, biology is so seasonal that it has productivity, it dies, it rots, it respires, and so I wonder how is that all globalized in your estuarine metabolism term?
well, the only thing for now I have looked at is the Galveston Bay. If you remember this decrease, long-term decrease in the chlorophyll, but then at the same time increase in the decrease of salinity, which means the increase in the fresh water. So my suspicion is that potentially because of this better nutrient management, so that you don't have so much of nutrient runoff, this way you create less of the algal blooms, right? So then this way, in the past there may be a lot of production, so CO2 could be lower, and then now without so much production, so CO2 would be naturally higher. Then combined with all these hydrological changes, then we see this very high increase rate of the PCO2 in Galveston Bay. So overall, the net ecosystem metabolism in Galveston Bay may be diminishing over the years, well, decreasing, not really diminishing.
Yeah, not sure, because there have been such marked changes, sometimes big step changes in the turbidity and in the nutrient inputs to the bay. So, and if it's too turbid, then algae don't grow. So
yeah, that's another thing. Well, let's see. Here in a lot of these Texas estuaries, because they're shallow, and then if it's windy, actually, I was talking with a student earlier before the seminar. One of the students actually came from Harte, went to study with Dr. Morowski. So then if people dive in these estuaries, if they have the experience, you can have your hand in front of the face. If in the water, a meter, you won't see anything. So completely pitch black.
No, but it would be interesting to have all I'm suggesting is to have a multidisciplinary approach to things, because it's not just physics and it's not just chemistry and it's not just geology. It's all of these things together, and they affect life. And the question is how does it affect life, and vice versa. Anyway, good to see you.
Yeah, thank you so much. Good to see you too. Bob?
Hi, Xinping. I enjoyed that. You measured multiple parameters, so I'm wondering if you're able to say anything about differences in the way that carbonate alkalinity and non-carbonate alkalinity behaved. You know how total alkalinity did. Did you see any differences in the patterns of carbonate and non-carbonate alkalinity?
Yeah, I was afraid you're gonna ask this question. So yeah, because really the agency, when they do the titration, they use a pretty simplistic method. And for us, the reason we didn't use absolute PCO2 value, rather we used the slope. The inherent assumption is that we assumed the organic, or non-carbonate alkalinity contribution stayed the same. So that's the best we could do, because really there was no information on how much non-carbonate alkalinity may be there in these estuaries.
Okay.
But that's a great question, and that's something we need to work on, in the future.
There are always many more things to do.
Yes, definitely.
Excellent questions. Any final question? I'm not seeing any other hands up. And so with that, thank you so much, Xinping. This was a fabulous presentation and really great questions from students and staff alike, and we really appreciate you joining us today. Thank you so much.
Thank you so much for having me, and I wish all you have a great weekend.
Thank you.
Thank you.
Thank you.
Thank you. Bye.
Thank you.